Welcome to this particular module, and in this module, as I promised, we will look at the Colpitts oscillator, right. In the last module what we have seen? We have seen the Hartley oscillator. So, when you talk about Colpitts oscillator and when you want to compare Colpitts oscillator with Hartley oscillator, what are the changes? What are the changes, right, in the circuit? So, if you really think about what are the changes, then you will see that it is exactly opposite of Hartley oscillator. That means, wherever the inductors were there, now we are replacing those inductors by capacitor. Wherever the capacitor was there in the Hartley oscillator, we are replacing by an inductor. That is why we say it is exactly opposite to the Hartley oscillator, right. So, now let us see the Colpitts oscillator. If we see the screen, and what we see, like the first sentence itself says that the Colpitts oscillator is the exact opposite of the Hartley oscillator, right. So, just like the Hartley oscillator, the tuned tank circuit consists of LC resonance, sub circuit connected to a feedback of the operational amplifier. So, here you see you have 2C, you have 1L. You have 2C, you have 1L. If you see just about capacitance, then this is nothing but your capacitance divider. You have seen a resistance divider, right. You have seen a resistance divider. Instead of resistance, I am using the capacitance. So, it is a kind of capacitance divider, right. Same circuit here, equivalent circuit or representative circuit. So, here the Colpitts oscillator uses capacitive voltage divider network, right, as the feedback source. The Colpitts oscillator uses a capacitive voltage divider network as its feedback source. Now, the two capacitors C1 and C2 are placed across a single common inductor, as shown in your figure, this figure. C1, C2 and L form the tuned tank circuit with the condition for oscillation being X1 plus X2 or Xc1 plus Xc2 equals to XL, which is same for the Hartley oscillator as well, right. There it was XL1 plus XL2 equals to Xc, here Xc1 plus Xc2 equals to XL. Now, depending on the impedance, the LC oscillators can be classified as Z1 and Z2 are capacitors, Z3 is inductor, it forms Colpitts oscillator. I have told you earlier also that if I have Z1 and Z2 inductors and Z3 capacitor, then it becomes my Hartley oscillator. If I have Z1 and Z2 as capacitors and Z3 as inductor, then it forms my Colpitts oscillator, right. As an inverting amplifier configuration is used in the Colpitts oscillator, gain depends on resistance values in forward path, right. We have inverting amplifier is used, gain depends on the forward path. A minimum gain of 2.9 is required to start oscillation. So, resistance must be chosen accordingly. Here the minimum gain is required is 2.9, all right. Now, two capacitors produce. So, now if I have two capacitors, it will produce a phase shift of 180 degree, right, 90 90 180 degree. So, alright. So, from here what we get is that if I use one capacitor, I have phase shift of 90 degree. If I use another capacitor, I have phase shift of 90 degree. So, I have two capacitors, I have phase shift of 180 degree, right. This is what we understand, okay, alright. So, two capacitors produce 180 degree phase shift, that is gain shifted by 180 degree to produce the positive feedback, Why? Because we are applying the signal to the inverting amplifier, inverting terminal of the op amp. So, inverting terminal of the op amp, when we apply the signal, with our output would be 180 degree phase, the output phase would be 180 degree out of phase with respect to the input voltage or input signal. So, to have, we should have one more 180 degree gain phase shift, and this 180 degree phase shift is given with the help of two capacitors. The frequency formula is kind of similar, 1 by 2 pi root of L C, where here is C T, there in that one it was LT. So, here CT you can see here. So, we can write CT is C1 in parallel to C2, correct, C1 in parallel to C2. Thus, we now know that here in Colpitts oscillator the phase shift is given by capacitors and the formula of for frequency is nothing but f equals to 2 pi under root of LC. So, if I want to now solve a problem, right, how can I solve a problem for the Colpitts oscillator. So, for a given problem which is right now in front of you in this particular problem, what is the problem? A Colpitts oscillator circuit having two capacitors 24 nanofarad and 240 nanofarad. So, we have capacitors C1 equals to 24 nanofarad, we have capacitance C2 equals to 240 nanofarad, right, C1 equals C1, we have C2 respectively, and are connected in parallel with an inductor. Inductor is L equals to 10 millihenry, right. Then what we are asked to find? We are asked to find that determine the frequency of oscillation of the circuit, the feedback fraction and draw the circuit. Okay. So, we are asked to determine frequency, we are asked to determine the feedback fraction and we are asked to draw the circuit. So, let us do one by one. Now, we already know that when you talk about the Colpitts oscillator, the frequency formula is f equals to 1 by 2 pi under root of LC, and where C is nothing but CT. So, here CT is C1 parallel to C2. So, in that case I can write 24 nanofarad into 240 nanofarad divided by 24 nanofarad plus 240 nanofarad, which is equals to 21.82 nanofarad, right. So, I can get value of CT. Now, I can place this value of CT here. I have the inductor value L given here, I know 2 pi. So, from that I can find f. So, I put the value of inductor, I put the value of CT, this is CT, this is L, then I get value of frequency 10.8 kilohertz. Now, if I want to measure the Hartley oscillator frequency, which is lower frequency, we have to consider 1 by 2 pi under root of 1 m into 500 picofarad equals to 1 by 6.283 under root of 50 picofarad, which is 225 kilohertz. Yeah. So, again we are just talking about the comparison with Hartley oscillator. So, if I compare with Hartley oscillator, then I can see this change, alright, then I can see this change. This is why we are comparing, because what I thought is now we are comparing, that is why we have this values, alright. So, the frequency of oscillation for Colpitts oscillator is 10.8 kilohertz, which is here, within the feedback fraction is given by f, feedback fraction is C1 by C2, which is about 10%, alright. So, if I want to actually design the Colpitts oscillator, how can I design the Colpitts oscillator? So, you remember last time we have seen the Hartley oscillator using multisim, right, and we saw that how you can change the output, right, by changing the whether you can see the change in the output or whether you can see the change in the oscillation, or how can you change the oscillation. This everything you can do by changing the value of inductors in case of Hartley oscillator, while here if I keep changing the value of capacitors, I will again see the change in the output. So, here to get the signal at the output, instead of using breadboard and the components, we are again trying to show you using the multisim software. So, here what we have to see, here we can see that once we connect the circuit as shown in figure in multisim, which is figure number 18, right, we set value of R1 and R3 to adjust the gain, and if you have R3 equals to 3 kilo ohm and R1 equals to 1 kilo ohm can be used. Then what we have to see? We have to see the output at pin number 6 of the op amp, and then we can measure the frequency of oscillation with the theoretical value. So, theoretical value I am not calculating right now, right. We have seen the example, previous example, how you can measure the frequency of oscillation using the formula. What I want to show today here is how can you measure the output signal using the multisim. So, how we will design the circuit in multisim and how we will see the change in the output signal. So, for that let us again ask Sitaram to show it to us how can we design this circuit in multisim. When he is designing, I will show it to you what exactly we have designed. So, now if you see the Colpitts oscillator, it is similar circuit which is given to you as an example, right. It is similar circuit which is given to you as an example. So, now if you see that you have here two capacitors, you have here capacitor 1, you have capacitor 2, right, here and here you have one inductor, they have one inductor. So, whenever you see suddenly this kind of circuit, it should immediately strike you that, oh, this is a Colpitts oscillator. If you see two inductors and one capacitor, you will see, okay, this is a Hartley oscillator. Now, what he has done is he is measuring voltage here, which is right over here, he is trying to measuring voltage over here, and then he is looking at voltage at the output, right. Three things he is doing simultaneously. What I will ask him is show one by one. So, just show first output voltage which can be generated in terms of the waveform, and then we show second one, then we show third one, and then we show all three voltage simultaneously, all three signals simultaneously. So, now you see that he is using the split screen, and then here we can just remove or show. You have the on the right side you have the button where it says show and you have removed, right. So, if I add this, we can see signals, if I remove this, we cannot see the signals at the particular point. Now, if I am looking at the voltage and if I am running the oscillator, then I can again change the yes. So, you can see here the oscillations are there, again you can see the times per you can change the time per division to get the better idea. You can play with the tool and you can see that by changing the divisions you can see frequency increasing or the number of divisions are higher, time per division is higher, and now you can see both the things simultaneously. You can also see corresponding voltage at the output and how the oscillations are occurring with respect to that particular corresponding voltage. Now, if I see the voltage at pin number at the input somewhere where the two capacitors and inductors, right, at the feedback, then I can see the voltage as well. I can also see the voltage across the inductor which is right over here, and then if I want to see all the signals together, then I can see all the signals together as well. You see all the signals I can see simultaneously, which you can see right over here, right. So, this is again a beautiful way of understanding whether my circuit will work or not, and if it works, what is the voltage at what particular point. I can change the point, from here to another point if I want to do that. You see, if now we want to see the change at the inverting terminal of the op amp, we want to see the change in the voltage, the inverting terminal of the op amp, and then just let us see only that particular voltage. Yes. So, this is the voltage at the inverting terminal of the op amp, right. So, if I want to see the change, if I want to see the voltage over here, yeah, that is fine, it is the same voltage. You see the voltage at output, you can see it is same voltage which is right over here, this point, right, this point and this points are same, alright. So, you can see voltage at here which is here, here, here. So, you can just put number of points and you can measure the voltage at that particular point. So, easy way of understanding the things, but the difficulty will be when you actually implement the circuit. So, try to do both the things, first try to do the simulation and then try to do the experimental work, where you go to the lab and try to design your Colpitts oscillator. alright guys. So, this is how you can design a Colpitts oscillator, and this is the this is the end of the oscillator sections. When we talk about the oscillators using the operation amplifier, these are the Colpitts oscillator. Earlier we have seen Hartley oscillator. This Hartley oscillator and Colpitts oscillator both are the oscillators which are the tank oscillators or LC oscillators. Before that we have seen Wien bridge oscillator, before that we have seen RC phase shift oscillators. So, now you know how we can design phase shift oscillators, you know how we can design Wien bridge oscillators, you know how we can design the LC oscillators, whether it is Hartley or whether it is a Colpitts oscillator. And you also know, if I give you a breadboard to work with, then you can also design the circuit. If I give you the simulation tool, then also you can design the circuit, right. So, now you are able to have a better experience. I hope you have a better understanding of the oscillators, you have better understanding of using operation amplifiers using this particular videos, and you learn different things, you understand different things, and you also solve different problems. We have seen several problems in this particular module, right, that how we can design the oscillators, or if I ask you to calculate the bandwidth, or if I ask you to calculate the F frequency, high frequency and low frequency, how you can calculate it, right. So, this is the end of this particular module, and I will see you with new applications or other applications of operation amplifier in the next modules. So, till then just look at the video, right, see the video, understand the circuits that I have discussed, and if you have any questions, feel free to ask me your questions once you try it, right. So, this is the last slide for this particular module. So, I will see you in the next module. Till then, you take care. Bye.